Hello, friends. Welcome to Akulmach Live, and I like to welcome all space enthusiasts to a journey through cosmos, a quest for the pale blue dot beyond our own Earth, which is we would like to call Earth 2.0. For decades, the search for habitable exoplanet has been captivated our imagination. We have pointed our telescopes at the distant sun, hoping to catch the faint transient of a world similar to our sun. But what if I told you that our focus might have been slightly off? What if the key to finding another Earth lies around the brilliant sun like stars, but around their smaller, dimmer, and far more numerous cousins known as red dwarf? So, in this exploration, we will dwell into the fascinating world of red dwarf stars and uncover the compelling reasons why there are now considered as a prime candidate in our search for life beyond Earth. We will explore their unique characteristic, the potential habitability of the orbiting planets, and why the sheer abundance of these stellar bodies makes them an undeniable focus for future exoplanet hunting missions. So get ready, friends, to have your cosmic perspective shifted slightly as we explore the intriguing possibility that our galactic neighborhood might be teeming with habitable world orbiting these often overlooked stars. So before we dive into why red dwarfs are so promising, let us first understand what exactly they are. Red dwarf, also known as M dwarf, are the smallest and the coolest type of main sequence star. When I say cool, is actually about the temperature of the star. Think of our sun as relatively average size star, and now picture a star significantly smaller, less massive, typically about 0.08 to zero point 0.6 times the mass of sun. Very small comparatively, and with much lower surface temperature, usually below 4000 Kelvin. This cooler temperature gives them their characteristic reddish hue, hence the name red dwarf. The most striking feature of the red dwarf is their sheer abundance. They are by far the most common type of star in the Milky Way galaxy, making roughly about 85% of all the stars. This vast population alone makes them statistically significant in search for exoplanets. While large, brighter stars like our sun are certainly easier to observe, the sheer number of red dwarf dramatically increases the potential number of planetary systems available for study. Imagine casting a wide net. The more net you have, the more likely you are to catch something interesting. Red dwarf provide us with a astronomically large net in our cosmic fishing expedition. One of the most significant advantage of red dwarf in the context of habitability is their incredible long lifespan. Unlike larger, more massive stars that burn through their nuclear fuel relatively quickly, red dwarf burn their fuel with extreme efficiency. Their lower mass and temperature result in much slower nuclear fusion rates in their cores. As a result, red dwarf can live for trillions of years, potentially hundreds or even thousands of times longer than the stars like our sun. This extended lifespan offers a crucial advantage for the development of life on any orbiting planet. The evolution of complex life as we know it on Earth took billions of years. The planet orbiting short-lived star might simply not have enough time for life to emerge and evolve before their host star enters into death spiral. Red dwarf systems, on the other hand, provide an immense timescale for biological processes to potentially unfold. This vast cosmic timescale significantly increases the odds of finding a planet with life because it has ample time to arise and also diversify. And of course, a long-lived star is only beneficial for life if it has a host planet in its habitable zone. The region around star where temperatures are just right for liquid water to exist on a planet's surface. For hotter, larger stars like our Sun, this habitable zone is relatively far out. However, due to lower luminosity and cooler temperature of the red dwarf, their habitable zones are much closer in. This proximity has both advantages and challenges. On the plus side, planets in these closer orbits have higher probability of being detected using transit method, where we observe the slightly dimming of stars as a planet passes in front of it. Closer orbit means more frequent transits, making detection easier. However, this close proximity also leads to phenomena called tidal locking. Just as the moon always shows the same face to Earth, planets orbiting with the closer habitable zones of red dwarf are likely to become tidally locked. This means one side of the planet perpetually faces the star, experiencing constant daylight, while the other side remains in perpetual darkness. For a long time, scientists worried that this extreme temperature difference between the day and night side would make such planet habitable. The day side could become scorching hot while the night side would freeze. However, the current research suggests that these tidally locked planets might still be habitable. Sufficient atmospheric circulation could potentially distribute heat from the day side to the night side, moderating the temperature's extreme and allowing for liquid water to exist at least a part of the planet's surface. Furthermore, some models suggest that the cloud cover on the day side or ice on the night side could also help regulate the temperatures. We have already touched upon the incredible abundance of the red dwarf stars in our galaxy. This sheer number is massive, and it's an advantage in the search for habitable worlds. Even if the percentage of the red dwarf hosting Earth-like planets is relatively small, the sheer number of red dwarf means there could still be a vast number of habitable planets orbiting them. It is a number game, and the red dwarf offers us the largest playing field. Furthermore, a recent advancement in the exoplanet detection techniques have made it increasingly possible to find planets around these smaller stars. The transit method, as mentioned earlier, is particularly effective for red dwarf system because a planet transiting a smaller star causes proportionately larger dip in the starlight, making the transit signal easier to detect. So mission like NASA's Kepler and TESS, which stands for Transiting Exoplanet Survey Satellite, has already discovered numerous exoplanets orbiting red dwarf, and many of these are within the potential habitable zones of these stars. The James Webb Space Telescope will further revolutionize our ability to study the atmospheres of these exoplanets, searching for biosignatures, chemical indicators of life. While red dwarf offers a wealth of potential in search of Earth 2.0, they also present some unique challenges and considerations. One significant concern is the higher level of stellar activity exhibited by many young red dwarfs. These stars can produce very powerful flares, sudden and intense bursts of radiation that can be far more energetic relative to the star's overall luminosity than as compared to solar flares of our sun. These flares could potentially pose a threat to the habitability of the orbiting planet by stripping away their atmospheres or damaging any life on the surface. However, it's important to note that not all red dwarfs are equally prone to flaring, and stellar activity tend to decrease as the star ages. And furthermore, planets with stronger magnetic field might be able to deflect some of these harmful radiation. The presence of thick atmosphere could also provide a degree of protection. Ongoing research is crucial for understanding the long-term effects of red dwarf flares on planetary atmosphere and the potential for life to adapt or find refuge. Another consideration related to tidal locking is the potential impact on a planet's climate and geology. The lack of day-night cycle could lead to unusual weather pattern and potentially affect plate tectonics, although more research is needed in this area. Finally, the reddish light emitted by a red dwarf would have significant impact on the appearance of any life that might evolve on their planets. Photosynthetic organism would likely need to adapt to utilize the different wavelengths of light available, potentially resulting in vegetation with color different from green as we see on Earth. This doesn't necessarily preclude life, but it highlights that the fact life on red dwarf planet might look quite different from what we are familiar with. Despite these challenges, the potential rewards of finding habitable planets around red dwarf are simply too significant to ignore. The sheer abundance of these stars, combined with their long lifespan and increasing capabilities of our planet hunting telescope, has led to growing consensus within the scientific community that red dwarf would be a primary focus in our search for life beyond Earth. Future missions and ongoing research are specifically targeting the red dwarf systems, and ground-based telescopes are continuously surveying the skies for transiting exoplanets around their stars. Space-based telescopes like TESS are specifically designed to conduct wide field survey, with significant portion of their observation dedicated to monitoring red dwarf. The James Webb Telescope, on the other hand, with its unprecedented ability to analyze exoplanet atmospheres, will play a crucial role in characterizing the planet discovered around the red dwarf and searching for biosignatures. Furthermore, there is an increasing interest in developing dedicated missions specifically designed to study red dwarf system in detail. These future endeavors will provide us with much more comprehensive understanding of the planets orbiting these stars, their atmospheres, and their potential for habitability. In conclusion, now, the paradigm in our search for Earth 2.0 is shifting. While the allure of finding a planet orbiting a star exactly like our Sun remains strong, the compelling evidence increasingly points towards red dwarf as the most promising hunting ground. Their overwhelming abundance, coupled with their immense lifespan, provide a vast number of opportunities for habitable planets to exist, for life to potentially emerge and evolve over vast cosmic timescales. While challenges such as tidal locking and stellar flares require careful consideration, ongoing research and technological advancements are providing us with tools to better understand these systems and assess their true potential for hosting life. As we continue to explore the cosmos, it's highly likely that our search for another Earth will increasingly focus on the faint reddish glow for these small stars. The key to unlock the secrets of life beyond our solar system might just lie in the numerous small and long-lived red dwarf and that populate our Milky Way galaxy. So thank you for joining me on this cosmic journey, friends. Keep looking up, and who knows what wonders the next generation of our telescope will reveal in the intriguing realm of red dwarf stars. Catch you again in the next one.